can start. There are already 9 people here. So I welcome you all to the 8th week. So last class we discussed about we started complex analysis where we discussed about some analytic functions, water analytic functions, and then how you could just go through the problems which come in GATE exams. And we also went through the introduction of the what is Cauchy integral theorem and all those things. Now in this class, I'll be discussing another important aspect of complex analysis, which is finding poles and singularity and those kind of things. So to start with, I will just give a brief introduction, and then we'll solve a couple of questions on GATE exams. Okay, so start with okay. Let me do it full screen. Yeah. So suppose you have any complex function f of z, and which is written in this form: a upon z minus z naught to the power n, where n is it can be anything 0, 1, 2, 3 up to infinity. So in that case, suppose you have this function and the function fz is analytic, or you all know being analytic means it's differentiable. If a function is analytic and differentiable at all points except at z is equal to z naught, because if as soon as you put z is equal to z naught, this function will become a upon 0, which is infinity, so it blows up at z is equal to z naught. Therefore, z naught is called the singular point. So the point at which the function becomes non-analytic, that point is called the singular point. So for this function, z naught is the singular point of fz. And it's also called, you can also call it pole of this function, and n is the order of the pole. So this is simply, you have been given any function, then how you could find, you just equate denominator is equal to 0, and then you would find the poles and the order of the pole. So there are different classes of singularities. So first is isolated singular point. So as the name suggests, it is isolated. That means suppose if z is equal to a is a singularity of fz, some function fz, complex function fz, and there are no other singularities, within a small circle surrounding that, within a small circle surrounding that point. These are just definitions, so it's not very important, but you could just, for the sake of continuance, you can just. So if you have some function and fz, and it is a singular point exists at z is equal to a, then and if there are no other singularities which exist within a small circle surrounding that point za, then that singularity is called the isolated singularity. Said to be isolated singularity of function fz. Of function f of z. So for example, you have some function f of z is equal to 1 upon z minus 1 or z minus 3. In that case, you could say that it has isolated singularities at z is equal to 1 and z is equal to 3. Because you can always take some very small point close to 1, and you can say that there are no other singularities which exist close to 1. So Yeah, in this way, this is called the isolated singularity. And then when it comes to solving questions, then there are many times when question comes when you've been given some function, you're asked to, you have been asked whether it's a singular, which kind of singularity it is, whether it is essential singularity or simple pole or singularity, removable singularity, those kind of things. So the another concept is essential singularity. So what does it mean? So I will not go into details of what are these, but I will just tell you how to find, how you can find that whether given a function, how would you say that okay, this is essential kind of singularity, or this is simple, or this is removable singularity. Suppose you have any function, and it is in the given form, 1 upon z minus z naught. Z naught is a singular point. That's 1 upon z minus z naught square up to n, z minus z naught to the power n. So in this case, this function has infinite number of negative powers, that is from 1 to n. So it has infinite number of negative powers. In that case, maybe it will go up beyond n also. It has infinite numbers of negative powers. In that case, you would just simply say that z is equal to z naught is called an essential singularity of fz. Now, another kind of singularity is removable singularity. It is very important. I will solve a couple of questions which came in GATE exam related to this. So it will be clearer much. It will be much clearer when you solve the question. So this is another important class of singularity, removable singularity. So it has two properties.
Sir,
Yes.
can you tell the essential singularity again? I couldn't hear it.
Essential singularity. Hello.
Yes, sir.
Okay, suppose you've been given any function and it has infinite power of negative power. By what I mean is that suppose here you have 1 upon z minus z naught to the power 1 plus 1 upon z minus z naught to the power 2 up to infinite number of powers are existing for z. So if you have this kind, if you can see this kind of function, then you could say that okay, at z is equal to z naught, fz is having essential singularity. There are no positive powers of z. What I mean, suppose there is no some nothing like this, z minus z naught to the power 1. There are no this kind of things. These are negative powers, right? 1 upon z minus z naught. You can write this form, z minus z naught to the power minus 1 plus z minus z naught to the power minus 2 up to infinity. So if you have any function which has this kind of structure, then you could easily say at once then okay, this function has essential singularity as z naught. Okay.
Okay, sir.
Excuse me, sir.
Hmm?
I didn't attend the previous class. What is Z not here?
Z naught is a pole. Suppose if you take this function, fz is equal to 1 upon z minus 1, z minus 3. So you equate the denominator. Okay, let me tell you. So if you have any complex function fz, said to be analytic if it is defined at all points. For example, this function is defined at all points except at z is equal to 1 and 3. Because as soon as you put z is equal to 1 in this function, it will become 1 upon 0, which is infinity. It is not defined. Okay.
Okay, sir.
Similarly, z is equal to 3 also this function is not defined. So z is equal to 1 and 3 are called the poles of the function. That is z not here.
So in the given function, there is only one pole you're defining.
Yeah, suppose in the question they will ask that please does this function have essential singularity at z is equal to 0, or this function has removable singularity at z is equal to 0. They will give a particular pole and then they will ask you that which kind of singularity it has.
Okay, sir.
Okay. So removable singularity is another class of singularity. So one of the important properties is that suppose you have been given some function and it has some pole at z is equal to z naught. So if that function satisfied this property, limit z tending to z dot fz is some finite value, then you say that this function fz has removable singularity at z is equal to z naught. At z is equal to z naught. And another important, there are two different ways through which you can find this. Another way is that you will expand that function in Lorentz series. I will tell you later in the class how to do that. And if in Lorentz series there are no negative powers of z, no negative powers of z minus z naught, then you say that the function has removable singularity. So two things which you can remember. If a Lorentz series expansion, if there are infinite number of negative powers, that means it has essential singularity. And if it has no negative power of z minus z naught, that you can at once you can say that it has removable singularity. So let us solve some questions so it will be clear to you. So suppose you have function sine z by z. Now they will ask that does fz has which kind of singularity? Which kind of singularity at z is equal to 0? So you can just, so you know that at z is equal to 0, this is this kind of form. So at once you have two ways. Either you can use first formula that limit z tending to 0 fz. You find this. If it comes out to be some finite value, then it means that it has removable singularity. So if you just do this, limit z tending to 0, sine z by z, it is 0 by 0 form, so you can apply L'Hopital's rule. You all must be familiar with what is L'Hopital's rule. So you differentiate both numerator and denominator 1. So it will become cos z by 1. Now you put 0. So cos of 0 by 1. So it is 1, which is a finite value. Therefore, your function sine z by z has removable singularity at z is equal to 0. So this is one way through which you have find that okay, this function has removable singularity. Another way is by expanding it. So you know that sine z can be written as sine of x. You know it's z minus z cubed by 3 factorial plus z to the power 5 by 5 factorial minus z to the power 7 by 7, so on and so forth to infinity. So so it will become 1. You put z inside, so minus z square by 2 factorial plus z to the power 4, so on. So what I told is that for a removable singularity, first find the Lorentz series expansion and then find if there are any negative powers. If there are no negative powers, then it is removable singularity. So you see that this function has no negative power in z. It has only as positive power 2, 4, 0, z to the power 0. So it is only positive powers. So in this way you can say that okay, this function has fz has removable singularity at 0. So okay, so you can use either of the two ways to find that whether a function is removable singularity or not. Is it clear?
Yes, sir.
Okay. So now I will just solve one question gate. I would ask you people also. You people can also try. Okay, I think this question. Okay, yeah, this question only. So you have been given some function. This question came in GATE 2010. So the question is for a complex function f of z, which is equal to exponential root z minus exponential minus root z upon sine of root z. Which of the following statement is correct? So there are 4 points, and you have to find that which one of this is correct. Either it is a removable singularity, essential singularity, or it is simple pole, branch point. Branch point is something which is I'm not going to teach in this class. If you want some of that, I would recommend you to go through my slides of the previous phase. It's not very important for GATE exam. So okay, so to solve this, you just use that property. Limit. They have asked at z is equal to 0. So the pole is at z is equal to 0. So limit z tending to 0 fz. You find this. You can also solve with me. If someone gets the answer, you can just tell me. So you just differentiate it by, because it's 0 by 0 form, so it is 1 by root 2 z exponential root z plus 1 by root. I'm differentiating both numerator and denominator. Upon 1 upon 2 root z cos of root z. Now put z is equal to 0. This will cancel out 1 by root 2 z numerator numerator. So left with 1 plus 1 upon cos of 0, which is 2. So you get a finite value. So limit z tending to 0, fz is some finite value 2. So the correct answer at once you will say that z is equal to 0 is a removable singularity. C option is correct. So in this way you can just find out that what kind of singularity it has. Is it clear?
Yes, sir.
Hmm. Now, okay, now I will just talk about some other properties. Okay, so Lorentz series, Lorentz theorem. So if you are required, to expand some complex function fz about a singular point, that is a point where fz is not analytic, then it is expanded by Lorentz series expansion. So general form of any function is, if you expand it, can have this form. This is general form. Z minus a plus a2 z minus a whole square. These are positive powers, and it can also have this kind of structure, z minus up to infinity. So this is a general form in which any Lorentz series expansion can be written. And if you put z minus a is equal to t, so this will become f of t plus a naught plus a1t plus a2t square plus up to infinity plus b1t plus b2t square up to infinity. And now this coefficient of 1 by t, the coefficient of 1 by t in a Lorentz series expansion of any complex function is a very important term. It is called the residue of the function. So residue of a function at point a naught. So residue I will be covering little later. So basically what I'm trying to say is, suppose you are given some function and you want to find the order of the pole or pole, then how you can do it using Lorentz series expansion. So first of all, what you do is that you just you just 2 points, you expand the function, you expand any complex function in Lorentz series form, and second, find highest negative power on in Z. That will give pole and order of the poles and order of the pole. Okay, so understand, let us solve one question. So this question came in GATE 2015. So they're given some complex function f of z is equal to 1 upon z into z plus half cos of z pi. And they've asked that which one of the following statement is correct. So they basically asked what is the pole and where is the pole and what is the order of the pole. So if it was some simple function like this, then you could have easily said that it has two poles, 0 at minus 1 by 2. But it has also a cos of z pi, and cos of z pi. So whenever you, simple thumb rule is that whenever you get this kind of question where you have trigonometric function and algebraic function both multiplied together, in that case, you always try to solve this using Lorentz series expansion. So what you'll do is that you'll just as I told, first you have to substitute this z minus a is equal to t. So you will substitute here z plus half is equal to t. So it will become 1 upon t minus half, z plus half is t, cos of pi t minus 1 by 2. You're putting t minus 1 by 2 in place of z. Or you can also write it this form, t by 2, 2t minus 1. And this is cos of pi by 2 minus cos of pi by 2. Cos of, you can write this as, this thing you can write as cos of pi by 2 minus pi t. Cos pi by 2 minus cos pi t is nothing but sine of pi t. So you can write this as sine of pi t. Now you have this from t by 2. Write it as 1 minus t2 because you'll try to do some binomial expansion. So minus sign will come. I just replace 2t minus 1 is equal to minus 1 by t2. And sine pi 2 you also expand it. So it will become pi t minus pi cube t cube by 3 factorial, pi 5 t5 by 5 factorial, plus some high order terms. And now you just, because your aim is to find the highest negative power, so keep t inside and take 1 minus 2t and this take pi by t common here, so you're left with 1 minus pi square t square by 3 factorial plus pi 4 t4 upon 5 factorial. So what you have done is that I've taken this in numerator, taken pi by t common, and then again taken whatever left to the numerator. So now what I'm left with is, binomial expansion of this will be nothing but 1 plus 2t plus 4t square. Similarly, this will become 1 plus pi square t square by 3 factorial plus some higher order terms. Now this is the final, you cannot further simplify this equation. Now you need to find highest negative power in Z. So the highest negative power in Z is what? Okay, there is pi, there is this pi t square, so there will be one pi and t square has also come because there is pi t, so pi t square by 2. So the only highest power and highest negative power which you can get is this 1 times 1 divided by t, so only 1 by t square. Is it clear? Like, because rest of the term is higher power because t upon t square become 1 by t. So the highest negative power which you are getting in this series is 1 by t square. Are you with me? Is it okay?
Yes, sir.
Okay, so highest negative power is 1 by t square. So you simply now put again z plus half. T is nothing but z plus half. So you have poles. You have a pole at z is equal to minus 1 by 2. And the order of the pole is 2. So it doesn't have simple poles. It has a second order pole at z is equal to minus 1 by 2. So in this way, you could just find is that this function has at pole at z is equal to minus 1 by 2 and its order is 2. Is it clear?
No, sir. But why did you take the coefficient of 1 over t square rather than 1 over t?
Because after Lorentz expansion you have to find the highest negative power coefficient. Okay, you're confusing it 1 by t. 1 by t is not 1 by t, coefficient of 1 by t will give you the residue. That I will tell later. But here they have asked not residue, they have asked the poles and order of pole. So in order to find the poles and order of pole, you have to take these two steps. You first of all expand the function in Lorentz series and simplify it as much you can, and then you find the highest negative power in z. So in this, highest negative power is t square only, because t to the power minus 2, right? Rest all other terms will give you much like positive powers. Like for example, let us take second. So 1 into t square. So t square by t square is nothing but 1. Or you take 2t times 1 by t square. So it will 1 by t. So t to the power 1. So the highest negative power is t square only. That's why I've taken it to. Is it clear?
Okay, sir.
Mm-hmm. Now I will ask you to solve this question. This question appeared in GATE 2011. So similar approach. You have a trigonometric function and algebraic function. So you find that using Lorentz expansion. So you just could find the answer to it. You just start solving and type the answer in chat box. And I would also solve once I get some answers. So Amit has answered option C. Fz has a pole of order 2 at z is equal to pi. Any more answers? Amit, are you sure? Okay, so I'm not getting any answer. So let me solve this. So similarly, you could just put z minus pi is equal to t. So it will become t plus pi sine of t plus pi upon t square. Or you can write this. You can just separate this. So you can write this t plus pi by t square sine of pi t. So this is nothing but it will be sine of t only. So you can write this as sine t upon t plus pi sine t upon. I've just opened the bracket. Now you expand this. So it will become 1 by t. Sine t you can again write as t minus t cube by 3 factorial plus t5 by 5 factorial plus pi upon t square t minus t cube by 3. Now you just open this. So it will become 1 minus t square by 3 factorial plus t4 by 5 factorial infinity plus pi upon t minus pi t square by 3 factorial. So now this is the final expression. Now you find the highest negative power in t. So highest negative power in t is this, because rest are positive powers, t square, t to the power 4, t square. So in this case you have 1 by t, so t is nothing but z minus pi. So you have poles, z is equal to pi, and order of pole is 1. So if you just look at this question, then you could just put, so this is why I was telling that whenever you have trigonometric functions, so these things become a little complex, so you better always use this approach to find the correct answer. So otherwise, if you just directly put z minus pi by square is equal to 2, in that case, you would have got z is equal to pi in order 2. So it's confusing little. So it's better advisable to always, whenever you have trigonometric function on this, you first expand this and solve using this approach. Then you will get right answer. So option D is correct answer. Fz has a simple pole at z is equal to pi. Yes. Is it clear? Okay. Yeah, Aparna answered right. Nisha is also there. Yeah. So many right answers. Okay. So now I will just move to residues. So as I told little just couple of 5-10 minutes before, that in a Lorentz series expansion you have this kind of expression, then the coefficient of 1 by t term is called the residue of the function at that point. Suppose you have any function and it has singularity at a point, and you just did the Lorentz expansion of the function in this form, then whatever coefficient of 1 by t you will have, that will be the residue of the function at that. So this is not just one way to find residues. There are simpler ways also. So there are 2-3 ways of finding residues. The first is residue at simple pole, which is very easy. Suppose you have any function which has simple poles at a, simple poles at a, z is equal to a, then residue of that function fz at z is equal to a is limit z tending to a z minus a f of z. So if you have any simple poles and you have to find the residue at that pole, then this is the formula. Or suppose you have to find residue at a pole of order n. It is not a simple pole, but it is a high order pole. In that case, the more generalized formula to find the residue, suppose the order of the pole is n, then you have to use this one, then the residue will be given by 1 upon n minus 1 factorial dn minus 1 dzn minus 1 limit z tending to a z minus a to the power n f of z. So this is a more general formula, because if you just put a simple pole, that is for a simple pole n is equal to 1, for simple pole n is equal to 1, so this will just become 1 upon 0 factorial, this will become limit z tending to a z minus a fz, which is nothing but this. So this is a more general formula. So you could remember this if you have to find a pole of order n. So okay, so based on this formula, you can solve this question. Simple question. This question appeared in GATE 2013. This is a question of 41. So for a complex function f of z, what is the residue at the pole z is equal to 1? So you have to find the residue at pole z is equal to 1. So z is equal to 1 is a pole and the order is 2. Okay, so you can just, so residue of fz, z is equal to 1 is nothing but 1 upon, sorry, 1 upon n minus 1 factorial. So n is here 2. So you just put n is equal to 2 in this equation. So you'll get,
That limit is outside, I think.
huh?
That limit z tends to a is outside. Means first we differentiate, then we take the limit.
Yeah, that's right. Okay, okay. Oh, okay, okay. Yeah, it just, yeah, you're right. Sorry, sorry. Yeah, this limit will first you will differentiate and then you will took the limits. Yeah, thank you for correcting. Yeah. So 1 minus n, so 1 factorial, and then again just limit z tending to 1 d by dz of 16 z z plus 3 z minus 1 square and z minus a to the power n. Here a is 1, so z minus 1 to the power 2. It will just cancel out and then it's simple. Just differentiate it. So it will become z plus 3 whole square, z plus 3 equals 1 minus z. So it will become 16 limit z to the power 1, z cancel. So it will become 3 upon 1 plus 3 whole square, 16. So 48 upon 16, 3. So this is an entity type of question. So simply the residue of the function at this pole is nothing but 3. So it was a very fairly simple question. So if you just remember this formula, then you could have found it.
सर
Or if, hello, yes.
हेलो सर, यदि मान लीजिए हमारे पास जो पिछले वाला फंक्शन दे देता वो z माइनस पाई स्क्वायर वाला,
Hmm.
ठीक है, तो
Hmm.
उसमें हमने जो पॉल निकाला है उसकी अबाउट रेशिड्यू निकालना होता,
Hmm.
राइट? तो
Hmm.
सर उसमें उसको मतलब कैसे हैंडल कर पाते सर उस क्वेश्चन, उस टाइप ऑफ क्वेश्चन?
उसका
यस
रेसिड्यू,
सर, जेड
उसका रेसिड्यू सिंपली ये होता कोफिशिएंट ऑफ 1 by
हाँ
t.
यस सर.
हम्म. Or you could have also used this formula. Or you could have also used this. I've not tried it using this, but you can just try that whether using this formula also you can find it out. But then yeah, you can.
सर लोरा सीरीज तो तभी यूज करेंगे जब मतलब फंक्शन में कोई ट्रिगोनोमेट्रिक फंक्शन आ जाए, राइट?
Right. Generally, whenever you have some trigonometric function, ना, your Lorentz series you use करते हैं. Easier होता है solve करना.
Yes, sir.
Okay, so yeah, there is one other kind of function. For example, this has never come in gate for, but example you have been asked to find poles of a function. Which has this form. Suppose fz is equal to phi of z upon ratio. There are two functions. Fz is equal to phi of z divided by psi of z, and it has poles. Fz has some pole at a such that phi of a is not equal to 0, but psi of a is equal to 0. In that case, if you need to find the pole and the residue of the function, so that will be given by psi of a upon d psi a. Okay, or you can just write it as phi of a upon psi dash of a. For example, you have cot of z, and they have asked you how to find. You have been asked to find the residue of this function. So cot of z you can write easily at cos by sine, and you have asked to find the residue at z is equal to 0. So it has pole as z is equal to 0 because when you put the sine z is equal to 0, it will become, you can find. So this has this form because cos of 0, let me write this one, phi of z upon psi of z. Now here phi of 0 is nothing but cos of 0, which is equal to 1, which is not equal to 0. And psi of 0 is equal to 0. So you have this form where psi of a is equal to 0 and phi of 0 is not equal to 0. So in this case, your residue of the function will be so that is cos of 0 upon differentiation of sine z is cos z, so it is 1. So residue is 1. These are different ways, but I would recommend you to, whenever you follow only these two ways to find, like Lorentz series expansion, or this is very helpful in finding residues, or you can also use these two formulas. These, I will recommend you remember only these two things. This is important. And another thing is when you get a trigonometric function, then you use this Lorentz series function. You can try this also with cot z, also with Lorentz series function, you will get the same answer. You can try this cot z, cos z by sin z, you get the same answer. For example, let me do it only. So fz is cos z by sin z. So cos z is 1 minus z square by 2 factorial plus z to the power 4 by 4 factorial infinity. And sin z I'm taking above, or let me write here only. So z minus z cube by 3 factorial plus z to the power 5 by 5 factorial, so on. So you can again write this as 1 minus z square by 2. Neglect high terms because high order terms are not required. take z common here. So become 1 minus z square by 2. Z to the power 4 by 5. Now you take this above in the numerator. So you will have 1 upon z, 1 minus z square by 2 factorial. Z to the power 4 upon 4 factorial. And this will become 1 minus z square by 2 factorial. Plus higher terms. Oh, minus 1. Now binomial expansion, retain only first term is enough. 1 plus z square by 2. Now you find the coefficient of 1 by z. So the coefficient of 1 by z is what? 1, which is the you just open these two brackets, so you'll get the coefficient of 1 of z is equal to 1. So in this way, the residue of that function at z is equal to 0 is 1. So this is, I would recommend it you whenever you get any trigonometric function, you have take this approach, single approach, and then you can find the residue of the function. Is it clear? Okay, Chaudhary sir, at the end of the lecture, can you send the associated reading why we derive the polar expanded lawrence taking the highest negative power? Okay, sure, I will do that. I will find some and I will share that PDF or whatever I get. I will share that. This is clear. This question is clear. No?
Yes, sir.
Okay. Okay, so today we have covered only how to find residues, what are different kind of singularities, essential singularity, removable singularity, couple of questions on that, and then how using Lorentz expansion we can find the residue of any function at some poles, and then in next class we'll start the integration, contour integration, Cauchy residue theorem and those things. From next class, the most important part is that only, because you'll surely get questions in GATE exams from that topic. Almost every year you get, in some exam you get questions from that topic. So yeah, in next 1 or 2 class I will cover that, and then on the request of some of you, I would start Fourier transform again, Fourier and Laplace transform in the coming classes.
So where can I get the slides or recorded videos of the previous classes?
Who is asking?
Ashutosh.
Ashutosh. Okay, Ashutosh, you don't have the access to these slides. You joined later, no?
Yes. I want to like join. So
Just send me your email ID.
okay, at like via what?
Here only.
Where?
On the chat box you can type your email ID.
Okay, sure, sir.
And Chaudhary, are you able to access those PPT? Last class you were saying that you're not able to. I just checked. I think I have given the access.
Sir, I got access to your PPTs but I told that I was not being able to join your group.
Okay. Oh, you're not added in. You are in that group, right? Or not.
Sorry, sir.
I added you in that group, and that's why you are able to access the PPT, right?
Oh, I didn't knew. Actually, I am not accustomed to the Microsoft.
Okay, fine. But
I am
anyhow,
mainly accustomed to the Linux.
no, it's okay, fine. But you are able to see the PPT right now.
Yes, sir. I can see
Okay.
the PPT.
Okay. Okay. Thank you. So I will end today's class.
Thank you, sir.
Thank you. Okay, I will send you Nisha Singh. Okay, I will send to you.